Okay, today I'm going to start section 3.5. Section 3.5 is about cross product, and cross product is a special operation that you perform on two vectors, and it only works for R3. So cross product is not defined for R2, it is not defined for R4. It is only defined, it's an operation that is only defined for R3, and it has very, very beautiful geometric interpretations, and it will help us also understand one geometric interpretation for the determinant of a 3 by 3 matrix. So imagine you have this plane here, and also think of these two vectors that are parallel to this plane. So I'm going to write these two, draw these two vectors inside the plane. For example, you have a vector, let's say u, and you have a vector v, like that. So this operation, the cross product, is going to enable us to find a vector that is orthogonal to both these vectors, and the length of that is going to be the same as the area of this parallelogram that is determined by these two vectors. So you can see that these two vectors together, when you bring them to the same point, they define a parallelogram, and this parallelogram has a certain area. Yes? So the cross product is an operation which will give us a vector that is orthogonal to these two. So it will be a vector like that. It will be orthogonal to the plane that is determined by these two vectors. And how long that will be depends on the area of this parallelogram. So for example, imagine if the angle between u and v was smaller, then this parallelogram was narrower, and then this vector would be shorter. And the maximum area would be when these two vectors are orthogonal with respect to each other. Then the parallelogram becomes a rectangle, and that would be the maximum area. And so this is going to be u cross v. So the notation that we use is this for the cross product, and the direction of the cross product can be figured out using something called the right hand rule. So imagine that you use your right hand and you put your index finger alongside the vector u. So that's for the index finger. And then you put your middle finger along with the vector v. So that's for the middle finger. Yes. Then your thumb will show the direction of u cross v. So just try to do that. Imagine you use your right hand, you put your index finger along the u and the middle finger along the v vector, and then the direction that u cross v shows and is the same as the direction of your thumb. So your thumb shows the direction of u cross v. Now, if you can have also a vector that is orthogonal to both u and v in the other direction of the same length. So this vector here would be v cross u. So, and now you can try this. What happens if you put your index finger along v and your middle finger along u? So the middle finger along u, then your thumb will point down. So just to give you a recap of what I said, we are going to figure out a method, an operation called cross product, which geometrically will give us a vector that is orthogonal to both u and v. And in terms of magnitude, how long that vector is, it depends on the area of this parallelogram here that is determined by the two vector u and v. And whether it's pointing up or down, you can determine using your right hand. you put your index finger along the first vector, your middle finger along the second vector, and then your thumb shows the direction of the cross product. Okay, now let's take a look at how you calculate the cross product. Here's the definition. Any questions so far? Here's the definition. If U and V are two vectors from R3, then the cross product is defined like this. And what you see here, it looks as if it's a determinant, but we know that the determinant is a number. When we talk about cross product of U and V, it's going to be a vector. So what you have here is basically a way of memorizing the formula. Yes. And it's very easy to memorize if you think of it as a determinant like this. So we say U cross V is a determinant like this. We put I, J, K, the standard unit vectors in the first row. We put U in the second row. And we put V in the third row. And now imagine I want to expand the cofactor along the first row. If I want to expand the cofactor along the first row, I have to multiply I by the corresponding cofactor plus J times the corresponding cofactor plus K times the corresponding cofactor. Yes, but the cofactor for I is going to be this minor. Yes, so it's going to be U2, U3, V2, V3. So that would be this minor here. Just imagine if I omit the first column and the first row, I will be left with this minor here. So that times I plus J times the corresponding cofactor. And the corresponding cofactor for J is minus whatever the minor is, because don't forget the pattern, it's plus, minus, plus, minus, plus, minus, plus, minus, plus. So for I, it's going to be the same as the minor. For J, it's going to be minus the minor. And for K, it's going to be the same as the minor. Now, the minor for this position is going to be minus U1, U3, V1, V3, and then plus, so that times J. And then finally, the minor for this position is going to be U1, U2, V1, V2 times K. So if I just give you this, yeah, and then of course for each one of these, you can just use the arrow technique. It's going to be this times this minus this times this, I. So you get V2, V3, U2, V3 minus U3, V2 times I. Then you get minus this determinant, this times this minus this times this. And then you get times this determinant times K. So this times this minus this times this, as you can see here. But if I just give you this part and say, okay, just memorize this, that's going to be difficult. However, if you know how to expand the cofactor along the first row of a matrix, the only thing that you need to memorize would be this part. Because then you just expand the cofactor along the first row of this matrix and you get the answer. Again, I want to emphasize that the cross product is a vector. It's not a scalar. Yes, even though just for memorization purposes, we represent it like this. So let me give you an example, and you'll see it's very easy to calculate the cross product. So find the cross product given U is this vector and V is this vector here. So U is the vector 1, 2, minus 2, and V is the vector 3, 0, 1. So the cross product of U and V, U cross V, is going to be I, J, K, 1, 2, minus 2, 3, 0, 1. Okay, so it's going to be 2 minus 2, 0, 1 times I minus 1, negative 2, 3, 1 times j plus, so the minor corresponding to this position going to be 1, 2, 3, 0 times k. So it's going to be 2i. Now here I get 1 times 1 is 1, 1 minus minus 6, that's 1 plus 6, 7. So there is a minus here, so minus 7j. And finally, I get 0 minus 6, so minus 6k, which I can also write as u cross v is 2 minus 7, 6. Yes, is there a question? Is it clear how I got the u cross v? Now, this vector, yeah, question? So this vector is going to be a vector that is orthogonal to both u and v, and also in terms of the length, in terms of magnitude, the norm of this vector, the norm of u cross v, is going to be the same as the area of the parallelogram that is determined by u and v. Now, here we have this theorem that proves some of the statements that I just made. If u and v and w are vectors in R3, then u dot u cross v is going to be 0. So I'm gonna just do the diagram again. I said that if you have two vectors, u and v, then the cross product is going to be orthogonal to both of them. So the cross product is going to be orthogonal to this vector. It's going to be orthogonal also to this vector. So this is going to be u cross v. If they are orthogonal, then u cross v, if you multiply that by u using dot product, or u cross v, if you multiply that by v using dot product, you're going to get 0, right? Because two vectors are orthogonal to each other if and only if their dot product is 0. Then you have, so u dot product u cross v is 0, and v dot product u cross v is also 0. So part A and part B, they simply state that both u and v are orthogonal to the cross product. Part C is something called the Lagrange Identity. It says norm of u cross v squared is going to be norm of u squared times norm of v squared minus their dot product to the power of 2. Part D is a relationship between dot product and cross product. So if you have u cross v cross w, it's going to be u dot v dot w times v. And here what you have is a scalar multiplication, because u dot w is a scalar, it's a real number, times v minus u dot v, that's another scalar, times w. And if you have u cross v cross w, that's going to be equal this. So this is scalar times v minus this is scalar times u. So this is a way of writing u cross v cross w as a linear combination of v and w. Or you can write them as a linear combination of v and u. And these A, B, C, D, these parts of this theorem, they're very easy to prove just using the definition of the cross product. So, for example, part A, we know that the cross product is like having this determinant. So it's going to be minor of position 1, 1 minus minor of the position 1, 2. And here you get the minor of the position 1, 3. And when you do U times U cross V using the dot product, it's going to be U1 times this plus U2 times this plus U3 times this. But notice that what we have here is the determinant of a matrix that has two identical rows. So this is the same as having a matrix with two identical rows. Row 1 is U1, U2, U3. Row 2 is the same thing. And row 3 is V. So you agree that if you have a determinant of a matrix with two identical rows, that determinant is going to be 0. So part B can also be proved in the same fashion. That actually shows that when you have a cross product, the cross product is going to be orthogonal to both component vectors. Is the logic clear here for part A? We know the definition of dot product is you have to multiply the first component of U by the first component of U cross V. So that's what I'm doing here. And then the second component of U times the second component of U cross V, and the third component, and then you add them up. But when you do that, you can see this is basically a cofactor expansion along the first row of a matrix like this that has two identical rows. That determinant is going to be 0 for sure. So also the other ones, they can easily be proved just by using the some algebra and the definitions. So you just define U to be U1, U2, U3. You define V to be V1, V2, V3. You will have to use the definition of norm. You will have to use the definition of dot product. And you can easily show that this is going to be equal to that. I'm not going to go over there because if I do so, my lecture is going to be very long. But this is something that I'm telling you, you can easily prove it by expanding these expressions here. So verify part A and B of the previous theorem using vector in example 1. So I think I need to do that quickly again because I erased it. If I have I, J, K, and I have the vector U is 1, 2, minus 2, and the vector V is 3, 0, 1. This is going to be equal this minor, which is going to be 2. And this minor here is going to be 1 plus 6, 7, minus 7. And this minor here is going to be minus 6. Now, we can try this. If I multiply U and the cross product, or if I multiply V and the cross product, 2 minus 7 minus 6, I'm supposed to get 0. So let's try this. If I multiply these two, I get 2 minus 14. So for the first one, I get 1 times 2, 2, minus 14 plus 12. You can see that's 0. And if I do the second one, same thing. If I do 3 times 2 plus 0 times minus 7 plus 1 times minus 6, I get 6 plus 0 minus 6. That is also 0. So just showing you that the cross product is going to be orthogonal to both U and V. some other properties of the cross product. If u and v and w are any vectors in 3 space and k is a scalar, we're going to have these properties. So u cross v is going to be negative v cross u. So this is something that I explained at the beginning. If you have u cross v, you can use the right hand rule and your thumb is going to show this direction. If you do v cross u, then your middle finger, your index finger is going to be across v and your middle finger going to be across u. Then you get a vector in the opposite direction but exact same length. So that shows that u cross v and v cross u, these two vectors have the same magnitude, the same length, and in both cases the norm of these vectors is going to be the same as the area of this parallelogram, the parallelogram determined by these two vectors. However, one of them, they have exact opposite directions, so that one of them is going to be equal minus the other one. So you have this relationship between u cross v and v cross u. So u cross v and v cross u are vectors of the same length but opposite direction. We also have the distributive property. So u cross v plus w is u cross v plus u cross w. That's the distributive property. You have the distributive property from either side, from left or from right. So if you have u plus v cross w, that's u cross w plus v cross w. Part D says if you have a scalar times a cross product, then you can multiply k by u first and then multiply the resulting vector by v, or you can multiply the two vectors using cross product, then times k. It's going to give you the same answer. So if you have k times u cross v, you can do this operation first and then multiply by the scalar, or you can multiply the scalar by u and then cross it with v, or actually you can do it u cross kv. So all of these are going to be the same thing. So you can scale u and then multiply by v, you can scale v and then multiply by u, or you can do the cross product and then scale the cross product. You're going to get the same answer. If you multiply a vector by the zero vector using the cross product, you're going to get the zero vector in any order. And this is obvious from the definition, because if you have something like this I, j, k, and you have a row of zeros, and let's say u1, u2, u3, so this is going to be 0 times I plus 0 times j plus 0 times k, because of this row of zeros, all the cofactors are going to be 0. So the cofactor corresponding to this is going to be 0, cofactor corresponding to this position is going to be 0, and the same for this one. And if you do u cross u, the same thing will happen. You get the product of a matrix and itself using cross product going to be 0. That is also obvious from the definition. If I have u1, u2, u3, and then I have u1, u2, u3 again, then you can see that the first minor is going to be 0. The minor for j is also going to be 0, and the minor for k is also going to be 0. So you get the vector 0, 0, 0. Any questions? Okay, so here we have the cross product of the three standard vectors I, j, and k in different orders. And there is a very easy way of figuring out what each one of them is using this circle here. So you can just use the definition and see that if you multiply I and I, you get 0 because of this property here. But if you multiply I and j, you're going to get k. So for example, I is 0, 1, 0, 0, j is 0, 1, 0, and k is 0, 0, 1. So let's say multiply I and j. It's going to be I, j, k, 1, 0, 0, and then 0, 1, 0. And you can easily see that the minor for I is going to be 0. The minor for j is going to be 0. And the minor for k is going to be 1 times 1, 1. 1 minus 0, 1, which is k. So I times j is going to be k. So here you have for all the different combinations that you can have for I, j, and k. If you multiply I times k, you got minus j. And there is this circle here that will help you memorize that. Notice that the direction is I, j, k, and the direction is clockwise. So if you're multiplying these in the clockwise direction, you always get the next vector. So for example, you multiply I and j in this order, you get k. If you multiply j and k in this order, so j times k, you're going to get I. And if you multiply k and I in this order, so k times I, you're going to get the next vector, which is j. So this times this is going to give you j. But if you're multiplying them in the other direction, in counterclockwise direction, then you get minus the next vector. So for example, if you multiply j times I, so j times I, you're going to get minus k because you're going counterclockwise. So j times I going to be minus k. I times k going to be minus j. And k times j going to be minus I. So k times j going to be minus I. I have it here. And if you multiply each one of these vectors by itself, and generally any vector times itself using cross products, going to give you 0. So here it says, note that the direction of the u cross v can be obtained by the right-hand rule. I already explained that. One property that the cross product does not have is associative property. So if you have u cross v cross w, then this is ambiguous. Because if you do this one first, you're going to get one answer. But if you do this one first, you're probably going to get a different answer. So generally, these two are not equal. And here you have an example. So imagine I have I, j, and j in this order. I have I cross j cross j. Now, this is an ambiguous expression because I don't know which one to do first. If I do this one first, I times j is going to be k, and then k times j, k times j, that's counterclockwise, I'm going to get minus I. But if I have I, j, j, cross, cross, and I'm doing this one first, I'm going to get I times 0, I'm going to get 0. So you can see that this is not equal this. So that's just a counter example to show that there is no associative property when you have 3 vectors and you're using cross product. Any questions? Geometric interpretation of the cross product. I already told you what the cross product is. The cross product is going to be a vector orthogonal to both u and v, and the norm of that vector is going to be the same as the area of the parallelogram. It is easy to show that the norm of the cross product is the area of the parallelogram determined by u and v. So you can do that using the Lagrange identity. So the Lagrange identity, I showed you the identity up there. It's this identity here. Now, u dot v is norm of u times norm of v times cosine of the angle between them. So you replace u dot v by the definition. You can factor out the norm of u and the norm of v, and you get 1 minus cos theta squared, which is sine theta squared. So you can see that the norm squared is going to be equal this. On the other hand, if you have two vectors, u and v, and they form a parallelogram, and they have an angle theta between them, the area of this parallelogram is going to be, let's say this is norm of u and this is norm of v, is going to be base times height. So let's say height is h, and here you can see you have a right triangle. So sine of theta is going to be opposite over hypotenuse. Opposite is h, hypotenuse is norm of v. So you can see that h is basically norm of v times sine theta. So the area of the parallelogram is going to be base times height. That's going to be norm of u times height. So norm of v times sine theta squared, sine theta. So you can see that this formula and what we got over here are basically the same thing. So norm of u cross v squared is norm of u squared times norm of v squared times sine theta squared. I'm missing a squared here. So 1 minus cos theta squared is sine theta squared. I am missing a squared here in the notes, so please correct it. If norm of u cross v is norm of u squared times norm of v squared sine theta squared, then norm of u cross v is norm of u times norm of v times sine theta. Notice that sine theta is always positive in the first or in the second quadrant, and theta is always between 0 and 180 degrees. So it's either in the first quadrant and the third quadrant. So I don't need absolute value here. Yes. So you can see that this is equal the area of the parallelogram that is determined by u and v. So how can this help solving problems like this? Imagine you're given 3 points, P1, P2, and P3, and you want to find the area of the triangle that is determined by these 3 points. So let's say this is P1, this is P2, and this is P3. And these three, in the three-dimensional space, they form a triangle. And you may be asked to find the area of the triangle that is determined by these 3 points. So what you can do is this. You create a vector P0, P1, P2. You create a vector P1, P3. And these two vectors together, they form a parallelogram. Area of the parallelogram is going to be the norm of the cross product. P1, P2 cross P1, P3. So if you take the norm of that, that's going to be area of the parallelogram. So this is equal area of the parallelogram. But you can see that the area of the triangle is just half of that. So if you're looking for the area of the triangle that is determined by these three vectors, you can just do 1/2 of the norm of the cross product. Okay, so let's just do that. Find P1, P0, P1, P2, and P1, P3, and then cross them, find the norm, and then divide that by 2. That would be the area of the triangle. Okay, so P1 is the point 220. P2 is the point -102. And P3 is the point 043. The vector P1, P2 using terminal minus initial is going to be -1 minus 2 minus 3, 0 minus 2 minus 2, 2 minus 0, 2. And the vector P1, P3 is going to be 0 minus 2 minus 2, 4 minus 2, 2, and 3 minus 0, 3. Okay, now in order to find the cross product, P1, P2 cross P1, P3, I'm going to use the definition I, J, K, -3, -2, 2, -2, 2, 3. It's going to be this minor here. And the minor is going to be -6 minus 4. That's -10. And then the next cofactor, the cofactor corresponding to this position, is going to be minus the minor. So what is the minor? The minor is going to be -3 times 3, -9, minus -4. So -9 plus 4. That's -5. But minus, that's going to be 5. So +5. And finally, the cofactor for this position is the same as the minor, which is going to be -6 minus 4. That's -10. So now, if I find the norm of that, the norm of P1, P2 cross P1, P3, it's going to be root 100 plus 25 plus 100. So this one is squared plus this one is squared plus this one is squared. That's root 225. That's going to be 15. So that means the area of the triangle is that divided by 2, because the area of the triangle is half of the area of the parallelogram. Is everything clear here? Any questions? Okay, and next we have a definition for another operation, which is a combination of both dot product and the cross product. This is called the scalar triple product. If u, v, and w are vectors in 3 space, then u dot v cross w. So notice that first you have the dot product and then you have the cross product. So the way I memorize that is that first we learn the dot product, then we learn the cross product. And in the scalar triple product, it's the same order. So first the dot product, then you have the cross product. And of course, for this to make sense, you have to do this one first, because if I have u dot v cross w, it wouldn't make sense to do this one first, because if you do this first, you're going to get a scalar, and then a scalar, you cannot multiply a scalar and a vector using the cross product. So it wouldn't make sense. But just for clarity, we put braces, we put brackets around the U and the W, the V and the W. But even if there is no brackets, if I just put U dot V cross W, it only makes sense to do this operation first. So this is called a scalar triple product. Now, the scalar triple product is very easy to show that the scalar triple product, which is going to be a real number, because this is a vector and this is also a vector, and when you cross two, when you use the dot product for two vectors, you get a scalar. It's easy to show that this is going to be the determinant of a matrix which has U as the first row, V as the second row, and W as the third row. That is, if U is the vector U1, U2, U3, and V is the vector V1, V2, V3, and W is the vector W1, W2, W3, then U dot V cross W, it's easy to show that it's the determinant of this matrix, where U is the first row, V is the second row, and W is the third row. So the reason for that is, imagine if I ask you to do this multiplication, yes, the U cross V. So this is going to be U1, U2, U3 dot product, and then if you are multiplying the V and the W, yes, you have to do it like this. You say I, J, K, V1, V2, V3, W1, W2, W3. So the first component is going to be the minor corresponding to this position. So the first one is going to be V2, W3, sorry, V2, V3, W2, W3. The second component is going to be the cofactor corresponding to J minus that, because the second one is going to be minus the minor. So you have minus V1, V3, W1, W3. And then for the third component, it's the cofactor corresponding to K. So it's going to be V1, V2, W1, W2. But when you multiply these two using the dot product, you're going to get U1 times this. V2, V3, W2, W3, minus U2 times this one, V1, V3, W1, W3, plus U3 times the last component of the cross product, V1, V2, W1, W2. And if you look at this, you see that this is actually the determinant of this matrix expanded along the first row. Because if you want to expand the cofactor along the first row, what would you do? You would do U1 times the corresponding cofactor plus U2 times the corresponding cofactor, and plus U3 times the corresponding cofactor. Yes, you would get the same thing. So this is actually the determinant of the matrix U1, U2, U3, V1, V2, V3, W1, W2, W3. So let's do this example. Given that U dot V cross W is 5, you want to find this. So you know that U dot V cross W is 5. You want to figure out what 3W dot minus U cross V is. So this is how you do this problem. You say this is like having a determinant of a matrix where the first row is 3W, the second row is minus U, and the third row is V. So when you look at this, think of this as a row of a matrix, or this one is also a row of a matrix. This one is also a row of a matrix. Then I can factor out 3 from the first row. I can factor out a negative from the second row. I get negative 3 W U V. Now, what I know is this. I know if I have a matrix where U is the first row, V is the second row, and W is the third row, that determinant is going to be 5. So I have to bring this to the same order. So I need U on top. And if I swap rows, what happens to the determinant? By swapping rows, determinant gets negated. So I get 3 times U W V. I swap the first and the second rows. I'm still not there. I just need to swap W and V as well. But if I'm swapping the second row and the third row, I have to negate the determinant again. So I get negative 3 U V W. And this I know. This is 5. So I get negative 3 times 5. So the answer is minus 15. Any questions? So next example, it says show that. Yes?
I'm just confused. Where did you get the negative 3 in the beginning? I think I might have missed something. Where did you get?
Do you remember if you had this? If, for example, you have a, let's say you have 2A, 2B, 2C, D, E, F, G, H, I. You can factor out a 2 from the first row. You get, yes, the same as having 2A, B, C, D, E, F, G, H, I. When we were studying the properties of determinant, you can factor out one number from a row or a column. So here I have 3 times W. That's the scalar multiplication. So this 3 can be factored out. And I have a negative V, negative U. It's like a negative times the first component, negative times the second component, and negative times the third component. So that negative can be factored out. So I got this.
Okay, so that's given to you while you do the problem, correct? Is that like you were given like the 3W, negative U, and V? And
yeah. That's how I start. That's where I started. I wanted to calculate this.
Okay.
So that means it's like having a determinant of a matrix where this is the first row, this is the second row, and this is the third row. So I had to factor out the negative and the 3, and then I had to do swaps so that I am here.
Okay, thank you.
Sure. So I want to show that these 3 are all the same. So U dot V cross W, that's the same as having a determinant of a matrix where U is the first row, V is the second row, W is the third row. So you agree that if I do 2 swaps, that does not change the determinant. So for example, I can do 1 swap. Let's just swap the second row and the third row. I get WV, yes, and then I do another swap. W goes up, V, U goes here, and V stays where it is. And then since I'm doing 2 swaps, I go back to plus. Yes, so each swap negates the determinant, but if you're doing 2 swaps, then you have minus times minus plus. So it's as if you have done nothing. So now let's look at this one. Isn't that W dot U cross V? So we get this. Now if I have U dot V cross W, U V W, I can do another two swaps. So for example, let's say I cross the U and the V, I get minus, V goes up, U W, and then I'm gonna do another cross, another swap, keep V on top, I switch U and W. W goes here and U goes down. So now since I have done two swaps, again, determinant does not change. But if you look at this one, this is like having V dot W cross U. So I get this. Okay. Now, we are at the position to understand the geometric interpretation of the determinant in the 2 space and 3 space now. I'm going to prove to you that if you're dealing with vectors in R2, yes, so determinant of a matrix like this, for example, let's say V1, V2, U1, U2, if you have a matrix like this, then the determinant of this matrix is the same as the area of the parallelogram determined by these two vectors, the vector V, V1, V2, and the vector U, U1, U2. These are vectors from R2. They form a parallelogram. Let's say this is V and this is U. They form a parallelogram. I'm going to show you that this determinant, actually absolute value of this determinant, is going to be the same as the area of the parallelogram determined by these two vectors in R2. And then when you are in R3 and you're dealing with a matrix like this, U1, U2, U3, V1, V2, V3, W1, W2, W3, then you can think of the first row as the vector U, the second row as a vector V, and the third row as a vector W. And if you bring these three vectors from R3 together, you can have a form like this. So let's say this is the first vector U, this is the second vector V, and let's say this is the third vector W. And these vectors together, they form something called a parallelopipe. So these two form a parallelogram, and then the three of them together, they form a shape like this, which is called a parallelopipe. And I can show you that this determinant here, the absolute value of this determinant, because notice that the determinant could be positive or negative. That's why I say the absolute value of the determinant is going to be the same as the volume of this shape here. So in the two-dimensional space, determinant of a 2x2 matrix can be thought of as an area, and in the three-dimensional space, the determinant of a 3x3 matrix can be thought of as a volume of a parallelopipe that is determined by the rows of that matrix. So this is the theorem. The absolute value of the determinant, this determinant, is equal to the area of the parallelogram that is determined by the two vectors u and v, as I explained here on top. And the absolute value of this determinant here is equal to the volume of the parallelepiped determined by the vectors u, v, and w. So here we have the proof for part A. To prove part A, we need to use the fact that the cross product is the area of the parallelogram. So here also we are trying to show that this determinant is the area of the parallelogram. So definitely we have to use cross product. However, cross product is only defined for 3 space. Cross product is not defined for 2-dimensional space. We can solve the problem by choosing 0 for the third component. So imagine that u and v are vectors in the xy plane, but we want to depict that in the 3-dimensional space. So there is a third dimension z, but the vectors u and v, they are inside the xy plane. So what happens if I want to express this 2-dimensional vector in the third dimension, in the 3-dimensional space? I just use u1, u2, and then 0 for the third component. The same for v, v1, v2, and then 0 for the third component. Now, if I cross u and v, then the norm of that is going to be the same as the area of this parallelogram. Let's do that. If I cross u and v, I get I, j, k, u in the second row, v in the third row. And then you can see the cofactor for I is going to be 0. The cofactor for j is also going to be 0. You're left only with the cofactor for k. So you get k times the corresponding cofactor, which is this determinant here. Yes? So area is equal norm of the cross product. And the cross product is determinant of this matrix times k. Norm of that is going to be absolute value of the determinant times norm of k. But we know k is a standard unit vector, so the norm of that is going to be 1. So it's equal to that. I'm also here using this, that if I have norm of k, let's say v, that's going to be absolute value of k times norm of v. I'm using this. So that's why here you have absolute value of the determinant times norm of k, but this part is going to be 1 because k is a unit vector. And proof for part B, I want to prove that absolute value of this determinant is actually a volume. So a volume of the parallelepiped would be area of the base. So if you have a parallelepiped and you want to find the volume of that parallelepiped, the volume is going to be area of the base. So the area of the base would be the parallelogram determined by v and w times whatever the height of the parallelogram is. So the area, the volume is going to be area of the base times height. Now, we have a formula for the area of the base, right? The area of the base is simply the cross product of v and w. So it's the norm of the cross product of v and w. What about the height? The height is simply the projection of u along the cross product. Because what is the height? Height is the orthogonal distance from this point to the base. So since v cross w is orthogonal to both w and v, we can find the projection of u along v cross w and then find the norm of that. That would be the height. So it's norm of the projection of u along v cross w we have a formula for the projection. It's going to be the dot product of these two over norm of u cross v. Then these two cancel out. You get absolute value of u dot v cross w. But isn't this the scalar triple product? That is the scalar triple product. And the scalar triple product is a determinant. So that's going to be absolute value of the determinant of a vector, of a matrix, where u is the first row, v is the second row, w is the third row. So now you can see that there is a geometric interpretation to determinant. If you're dealing with a 2 by 2 matrix, it's the area of the parallelogram determined by the two vectors. And if you're dealing with a 3 by 3 matrix, then it's going to be the volume of a parallelepiped that is determined by the 3 vectors. Any questions? So imagine I ask you something like this. Prove that these 3 vectors lie in the same plane. Yes. So imagine that we have a plane like this in the 3-dimensional space. And there are 3 vectors, and these 3 vectors, they lie in the same plane. So vector 1, vector 2, vector 3, they lie in the same plane. How can you prove that they lie in the same plane? You just need to figure out the volume of the parallelepiped that is determined by these 3. If these 3, they lie in the same plane, then the volume of the parallelepiped is going to be 0. However, if one of these vectors stick out, so for example, if this vector was not in the same plane as these 2, yes, if it sticks out, then there would be a parallelepiped, and that parallelepiped would have a volume bigger than 0. Yes. So here we have this theorem. If the vectors u, v, and w in 3 space have the same initial point, then they lie in the same plane if and only if the scalar triple product, which is the same as this determinant, is 0. So here we have an example. Find the volume of the parallelepiped determined by these 3 vectors. So for example, if I show that these, if these 3 vectors, if they don't lie in the same plane, then they have a situation, we have a situation like this. We have vectors that don't lie in the same plane. So they would form a parallelepiped. And I would be able to get the volume of that parallelepiped by just calculating a determinant. But if these 3, they lie in the same plane, and I try to calculate that volume, I would get 0. So if I get 0, I know that it's a flat object and it has no volume. So that means that the 3 vectors lie in the same plane. Now let's look at this one. It says find the volume of the parallelepiped determined by these 3 vectors. So the volume is going to be the same as absolute value of the determinant of the matrix where you have the first row u as the first row, so 2, 1, minus 1, v as the second row, 3, 3, 1, and then w as the third row, 2, 0, 5. So this is just what we proved over here, that the volume of the parallelepiped is going to be this determinant. So now I can calculate this determinant and using any method that I like. I can use the arrow technique, I can use cofactor expansion, I can use row reduction. Let's just go with cofactor expansion. The determinant itself, I'm going to call it determinant of A, is going to be 2 times expanding the cofactor along the first row. 2 times 15 minus 1 times 15 minus 2. 15 minus 2 is 13. And then plus or minus 1 times this, plus minus 1 times this cofactor, it's going to be minus 6. So we have 30 minus 13 plus 6. That's 36 minus 13. It's going to be 23. And then the absolute value of 23 is also 23. So the volume is going to be equal 23. Is this clear? Okay. Show that these vectors, they lie in the same plane. If I want to show that the vectors lie in the same plane, I would do the same thing as I did for this one. If the volume of the parallelepiped is 0, that means that the 3 vectors are in the same plane. So let's just figure out what the volume of the parallelepiped is in this case. Volume of the parallelepiped determined by these 3 vectors is going to be absolute value of the determinant of this matrix, 2, 1, negative 1, 3, 3, 1, and then I have 1, 2, 2, 1, 2, 2. So for the determinant of this, first I find the determinant and then I find the absolute value. If the determinant is 0, then I know that the 3 vectors are in the same plane. So again, cofactor expansion along the first row, I get 2 times 6 minus 2, 4, plus 1 times, okay, the corresponding cofactor for this position is going to be 6 minus 1, that's 5, so minus 5, plus negative 1 times the cofactor for this position is going to be 6 minus 3, 3. So I get 8 minus 5 minus 3, that's 0. Okay, so that means the area of the parallelepiped determined by these 3 vectors is 0. That means, according to this theorem over here, that the 3 vectors lie in the same plane. Very good. Okay, we have a few more examples here to connect what we learned today with the previous materials about vector and parametric equations for lines and planes. Example 9. It says find a point normal equation for the plane passing through these 3 points. So the point A, 2, 5, minus 1, and the point B, negative 3, 2, 1, and the origin. And the origin is 0, 0, 0. What we need is a vector, is a point normal equation. It would be very easy to find a vector equation. So the vector equation would be OP is OP0 plus T1 V1 plus T2 V2. So it's going to be 0, 0, 0. I can use the origin for the point plus T1. The vector V1 can be OA. So 2, 5, negative 1 plus, for vector V2, I can use OB. So T2 times negative 3, 2, 1. So this would be a vector equation for the plane. However, it is asking us for a point normal equation for the plane. So imagine this is O, this is A, and this is the point B. So for the vector equation, I could just use the point O and then the vectors OA and OB as the parallel vectors. I could do that. However, if I need a point normal equation, then I just need to find a vector that is orthogonal to the plane. So imagine this is the plane that is determined by the vectors OA and OB passing through the origin. A normal vector for that plane would be a vector that is orthogonal to both OA and OB. I can use cross product for that, sure. IJK, if I just cross OA and OB, I'm going to get a vector that is orthogonal to both OA and OB. So I'm going to just cross OA and OB. I'm going to get this cofactor going to be 5 plus 2, 7. This cofactor going to be 2 minus 3 minus 1 minus 1, 1. And then for the last cofactor, I get 4 minus 15. 4 plus 15, that's 19. Just double check everything. 5 plus 2, 7. 2 minus 3 minus 1. Minus 1 is plus 1. And then for the last cofactor, I have 4 minus 15. 4 plus 15, 19. Okay. So the equation is going to have this form. 7. Let's just use O, 0, 0, 0. And the normal vector is going to be the vector 7, 1, 19. And I'm going to plug in the values into the formula. A times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. And if I do so, since z0 is, since p0 is the origin, I get 7x plus y plus 19z is equal 0. Okay, next example. Any questions about number 9? Don't forget, for a point normal equation, we need a point and a normal. So for the point, I use the origin, and for the normal, I use the cross product of OA and OB, because that cross product is going to be orthogonal to the plane. Imagine you have two lines, for example, 9. Imagine you have two lines in the three-dimensional space. If you have two lines in the three-dimensional space, these two lines, they could cross, or maybe they don't cross. Even if they're not parallel, they don't have to cross. So I just need to put two parallel planes so that you can see what I mean. Imagine these two planes are parallel, and we have a line that goes in this direction in the first plane, and you have a line that goes in this direction in the other plane. Even though these two lines are not parallel, they will never intersect, because one of them is in the first plane and the other one is in the second plane, and the two planes are parallel. So they will never intersect. So if you're given two lines, these two lines may be intersecting, may be parallel, may be not parallel and not intersecting. So in this example here, it says, find the point of intersection between these two lines, if any. So maybe there is no point of intersection, maybe there is. Let's try to find the point of intersection to see whether there exists a point of intersection or not. The first line, I can write it like this. I can write the first line as 0 plus 3t, 3 plus 2t, and negative 6 minus t. So that's line 1. And line 2, I can write it like this. 9 minus 3s minus 3 plus 4s and minus 9 plus s. For these two to have an intersection, there must be a point that is on both of them. So there must be a point so that 3t is equal 9 minus 3s. And 3 plus 2t is equal minus 3 plus 4s. And minus 6 minus t is equal minus 9 plus s. If I can find some t and some s so that this linear system has a solution, then I have found the point of intersection. But if this linear system has no solution, then there is no point of intersection. Let's see. I'm going to write that in the form of a standard linear system. So 3s plus 3t is equal 9. Minus 4s plus 2t is equal minus, if I move this to the other side, I get minus 3. And minus s minus t is equal, if I move this negative 6 to the other side, I get negative 3 minus 9 plus 6. So you see, I have a linear system with two equations, with three equations and two unknowns. If this system has a solution, then I have found the point of intersection. If it doesn't have a solution, then there is no point of intersection. Let's try to write the corresponding augmented matrix. I'm going to write this row first. So negative 1, negative 1, negative 3. And then write this row, 3, 3, 9. And then write this row, minus 4, 2, minus 3. And then I use row reduction. So minus 1, minus 1, minus 3. 3 times this to this, 0. 3 times this to this, 0. 3 times this added to this one, 0. Negative 4 times this added to this, 0. Negative 4 times this, positive 4 added to this, 6. Negative 4 times this, 12 added to this, 8 and 9. So next step, I multiply this by a negative 1. I get 1, 1, 3. And then I get 0, 6, 9, 0, 0, 0. I'm swapping the second row and the third row. So now you can see that this system has exactly one solution, because you're going to have a leading one here, you're going to have a leading one here. You have two equations. You have two leading ones and two unknowns. The s and the t are the two unknowns, and you're going to get two leading ones that will give you a unique solution. So I'm not going to continue from here because you know how to do it, but basically you get your s, you get your t, and you can plug the t into this, you get the point of intersection. If you plug in s into this one, you're going to get the same exact point. Is it clear? Okay, so two lines that are not parallel in 3 space, they need not have a point of intersection. As I just explained, you can have two lines. Let's say this line lies in this plane and this other line lies in the other plane, and the two planes are parallel. So the two lines will never meet. Such lines are called skewed lines. And if you have skewed lines, you may be asked to find the distance between the two skewed lines. And the distance between the two skewed lines would be the same as the distance between the two planes. So this is the last example. Example 10, yes. And you are given two lines, two skewed lines. So these two lines are such that they are not parallel, and they are also not intersecting. If you want to find the distance between the two lines, this is what you can do. You can think of, because you're given the line, you know a point from the line and you know the direction. So you know P1 and V1, the point and the direction for the first line. You know P2, V2, the point and the direction for the second line. You can find a vector that is orthogonal to both V1 and V2. For that, you only need to cross V1 and V2. You cross them, and you get a vector that is orthogonal to both V1 and V2. And if it's orthogonal to both V1 and V2, it will be orthogonal to the two planes. Now, the shortest distance between the two planes would be the norm of the projection of P1, P2 along the vector V1 cross V2. So let me explain that here. So imagine you have these two planes that are parallel, and you have one line here, you have one line here. Let's say P1, P2. If you just draw a vector from P1 to P2, and think of a vector that is orthogonal to both planes, like this one. And for that, you can use V1 cross V2. V1 cross V2 will be orthogonal to both planes. You can find the norm of the projection of P1, P2 along this vector. So that will be the projection, and the norm of that is the distance. So you can find the projection of P1, P2 along V1 cross V2, and then take the norm of that. That would be the distance. So in this example, it says find the shortest distance between the lines. We can take this to be P1. We can take this to be P2. We can take this vector to be V1, and we can take this vector to be V2. Just find P1, P2, terminal minus initial, we get the answer. You can cross V1 and V2 using the definition, you get that. And then you just use the formula for the projection, for the norm of the projection. We know the formula for the norm of the projection of U along A is going to be absolute value of U dot A over norm of A. So we use that formula, and we get the answer. So that would be the shortest distance between the two skewed lines. So this is the next optional example. In the previous example, find the points of closest approach. If you want to find the points of closest approach, so those points could be, for example, here and here. For example, point A on the first line, point B on the second line could be the 2 points that are the points of closest approach. Actually, in this diagram that I have shown, probably it's not necessarily P1, but generally, if you have a point of closest approach, then the vector AB would be parallel to the cross product. So that means the vector AB would be orthogonal to V1, and the vector AB would also be orthogonal to V2. That means this is going to be 0, and this one is also going to be 0. So that will help you find the points of closest approach. But since this is optional and my lecture has got really long, I'm going to let you think about this if you like. But the distance between two skewed lines, that's important. So you may be asked in the test to find the distance between the two skewed lines. However, finding the 2 points of closest approach, that would be an optional thing. Any questions? Okay, I'm going to end my lecture here. And for the rest of the time, I want you to work on the examples, work on the exercises from web work. In those exercises, I'm asking it, I have already opened the set. So let me just make sure. Yeah, 3.5. So these are all about using the cross product. Work on these exercises. Let me know if you need help. I'm going to give you 5 minutes to think about this problem here, and then I'll do it on the board. Okay, let me explain this. You have 3 points. Let's say P1, P2, P3. Yes. And these 3 points, they determine a plane. So imagine you have the vector P1, P2 and the vector P1, P3, which you can calculate using terminal minus initial. Then if you cross these 2 vectors, P1, P2 and P1, P3, if you cross them, you're going to get a vector that is orthogonal to both of them. So like this. That is orthogonal to P1, P2 and orthogonal to P1, P3. And that vector could serve as the normal vector for the plane. Is that clear? When it says find a vector normal to the plane, that means a vector that is orthogonal to the plane. So let's calculate P1, P2. That's, let's say this is P1, this is P2, this is P3. So 6 minus 1, 5. Minus 4 plus 7, 3. 9 minus 8, 1. P1, P3. 6 minus 1, 5. Minus 3 plus 7, 4. And then you have 11 minus 8, that's 3. Okay, I'm just going to cross them using the formula I, J, K, 5, 3, 1, 5, 4, 3. It's going to be, so the cofactor corresponding to I is going to be 9 minus 4, 5. The cofactor corresponding to J is going to be 15 minus 5. That's 10, but I have to negate that, so negative 10. And the cofactor for the last one is going to be 20 minus 15. And 20 minus 15, that's 5. So it could be 5 minus 10 or negative 5, or any scalar multiple of that, because notice that any scalar multiple of this is also going to be orthogonal to the plane. So for example, if n is this, half of n, or a quarter of n, or negative 2n, all of them are going to be orthogonal to the plane. So the one that actually matches this would be negative this. So negative that is going to be negative 5, 10, negative 5. Actually, if I had multiplied this 2 in the other order, I would get this one. And so if I just multiply them in this order, I get this. If I multiply them in the other order, I get this. So, but this is the answer because it's asking me for the first component to be negative 5. So 10 minus 5. Any questions? Okay, so let's call it a day. Work on these exercises, and I'll be willing to answer your questions next time. Any questions for me now? Okay, then.